Team Gary coming at you live with Science 9 in the AM. I'm your host, Joel Sundar. We left off yesterday talking about direct current. Batteries flow in one direction through the circuit. Batteries are usually a source of DC, direct current energy. I have a diagram there, and on the diagram, a battery, a wire, and this little star represents something using the energy, perhaps a light bulb, going through. Jot that down if you haven't already. I'll pause the video while I update this. I'm going to move it like as in, this was actually from yesterday other than the diagram, a simple diagram. You can turn around. Square your shoulders up, yeah. Okay, anyways. So, just like the old person's rock band, AC, DC, right? So the other type is AC, alternating, not air conditioning. Second type. Oh, right. Thank you. What I see on my screen wasn't what you saw on there. Alternating current. Electrons flow back and forth in the circuit. Plug-ins, not plug-ins, are a source of AC electricity. I'm using common language too with these things. So jot this down, and you can see this here. I plug in a lamp or something like this. That's a very simplified drawing, but just to get across that, that's what we're talking about. When you plug something in, that's an AC source of energy. Pause the video so you can jot that down if you're on internet. While you're jotting that down, I'm going to just slide up to the next thing too. Current is measured with something called an ammeter. Ammeter, because amperes, we just call it amps, is the unit of measurement. So jot that down. All right, moving along. Something called resistance, because it was called volts, currents, resistors. That's our presentation title. Okay. Resistance describes how electrons are slowed down in an electric circuit. The unit of resistance is the ohm. Looks like the Lululemon symbol. It's actually a Greek letter, omega. The more resistance an object has, the harder it is for electricity to pass through it. There's going to be more, but I'll give you this chunk first. Spelling error is noted. Electrons. Okay. I will reveal everything now. Just a second. The harder it is for electricity to pass through, the more resistance an object has. And the applications, there's a ton of them. You might have heard of resistors if you're doing something in electronics, but here's just a couple. Controls for your stove, power levels on your microwave. Oh, there's tons, man. There's more. Yeah. We're doing some notebook days here, that's all. Anything where you can change the amount of energy being used is probably controlled with a resistor. And there's variable resistors like an up or down, like you can increase or decrease the amount of energy your device receives. We'll just leave it at that. Probably to do with resistance, because you might be wondering, why would you want to slow down the flow of electrons? That's a reason why. Any questions about just resistors in general? Now, I want to keep something in mind too. We're doing this instead of me just saying read the textbook page 700 through 800 or something like this and make notes or something, right? You still have to get some stuff down and read some stuff, but sometimes I just pick it out for you. Anyway, so that we can rush through it a bit quicker. And this way we have more time for activities, is what my whole point. So yes, we do have bookwork days. We're having a few in a row. Anyway, any questions about resistors? Have you guys ever heard of resistors before? Like electrical? Yeah, what? Oh, yeah, yeah. Well, just take a look at, you know how sometimes some plugins, and I'm just showing you my computer thing here. If you look at this and you read the fine print on here, it'll usually tell you what it's changing the amps or the volts to, the adapters. You know how a lot of plugins have a big fat plug-in end, like it's a thin cord, right? And then usually that's doing something to change the energy going into your device, because you just plug it straight in, it would, without that adapter, it would deliver too much energy. So there's maybe a resistor involved with that too. And it's probably not variable, it just does one. Like whereas a stove, you know, high or low. Now this is assuming it's an electric stove. A gas stove wouldn't need a resistor. Yeah, I actually have a gas stove too. Okay, then I will move it on a little bit here. We're going to get to a point where we need to do some activities. So if we were reading in the textbook, then we talk about just what is meant by a battery, and it's an electrochemical cell. Electricity, chemistry combined, you know, chemicals to provide electrical energy. Okay. Any battery must have something called an electrolyte, which is a liquid or paste that contains chemicals, often an acid. Often, okay, an acid. Batteries also need electrodes, the positive and the negative, and they're two different metals. Copper and zinc are the kind used on Duracells and stuff, the copper too. Batteries are wet cells if they have a liquid electrolyte. Car batteries actually have liquid sloshing around in there. And I'll pause it here. The dry cell is the next thing to keep it. I guess, no, to keep you like really on the edge of your seat. What's next? Somebody mentioned too, a battery must have an electrolyte, the word electrolyte, liquid or paste that contains some chemicals. Then I was just asked by someone, doesn't Gatorade advertise they have electrolytes? Yes, they do. And actually electrolytes are necessary in your body. They're usually positive or negative ions. They usually focus on the positives, potassium and stuff like this. And they're totally necessary in your body. And you know what? Your nerves have electrical signals in there, and your body processes these positives and negatives and sends them to the right place. And we won't get into the biology behind it, but yes, totally because of electrical signal. Yes, Nicole. You could, but you might not do well. Don't eat batteries. Yeah, it's not the kind of electrolytes you need. You might really hurt yourself. No. I have no idea, and when I say you could, it's just like you physically could. Do not recommend it, and it's not even not recommended. Don't. So you shan't. You shall not eat batteries. Let's just be silly now. Okay. Which is fine. It's my class. But as long as you guys realize, no, don't eat batteries. Electrolytes are not the same necessarily. That you need to consider. All right. So far, is there any examples? Or examples, I mean, any questions about it? Well, a wet cell is, the car battery is the best example. And you should never tip a car battery on its side, for example, because it is a wet cell. It can leak acids. I grew up on a farm, so we used to have a lot of batteries sitting around, and we had an old battery, car battery kind of thing sitting around. I remember moving it, and it had cracked the actual plastic shell around it and stuff, and got on my pants. And within a week or so, the pants, the acid had eaten through them. I threw them out. They're old work pants, but yeah, the acids aren't good. It's sulfuric acid, and there's lead plates inside it and stuff like that. Anyways, it's nasty stuff. Do not open up a car battery, and definitely don't eat them, as questioned before. Uh-oh, what did I just do here? Well, there we go. Batteries, okay, are dry cells if the electrolyte is a paste. Double A batteries, triple A batteries, and, you know, little Duracell kind of things, C batteries, D batteries, 9 volts. Those have a paste in them. That means you can twist them upside down and stuff like this. They're not going to leak. That's a good thing. And that's why they're used in electronics. I don't recommend opening them up too. I've opened them up too as a kid, but I saw them happen. But it is acidic. It is harmful. And there could be nasty stuff that you shouldn't be exposed to. It depends on the battery. So I don't recommend it. at all. Okay, I am going to move it. Now, we're going to do an activity right after this. Other terminology, though, about batteries. Primary and secondary cells. A primary cells, if you come across that term because it's science class, it means it's a dry cell that can't be recharged. Just a normal, I'm not advertising for Duracell, but it's the most common. Energizer, Duracell, no-name brand batteries, whatever. Secondary cells are rechargeable dry cells. Hey, rechargeable cell, your cell phone battery, right? Every night you plug it in, maybe halfway through the day you've used up all the juice. You know about recharging batteries. I'll pause this or freeze this. Okay, are we good with this? Almost. Okay. There's a little activity in the book, but we're not going to write it out as a full-blown lab, but it's because we don't have enough sinks to do it each individually. It's more of a demonstration. I'll pause. Okay, as mentioned from the textbook, we're not doing an, oh, frozen. Second. Not out now. All you're going to write down is the top, page 246, modeling voltage current resistance. You're not going to turn to page 246 because I'm going to just put it on the board here. So, study question, materials, procedure, you don't need that. That's why I put a line through it. You're just going to collect data. I'm going to talk to you about that in a second. So write down 246, just so you know where it's from. We're going to read through it as a group, and we're going to think about this as we collect the data, and eventually you will need to write down, yes, the chart. Eventually, why not right now? I'll pause. Yeah. Can you guys read that? Is it too small? You're up close. Now, I have expanded the size of the chart above the chart, just so you can read it easier to copy into your book. But make it look like this on the bottom, just one line. Water on, full, pinched. We'll talk about that too. We'll add that. And you can see I got this tube, etc. It's very simple, and this is why we're not doing a full-blown. But we'll read the textbook why we're doing this. Okay. Hopefully you've got this down. I've waited for a while. I'm going to flip to the textbook, and I'm going to. This is the actual page that I referred to. Taking a look. Modeling. Okay, guys. Modeling voltage, current, and resistance. A physical model can help you understand a process or object that may be hidden or too large or small to view directly. Models can be mental. Don't get me started about mental. Mathematical or a combination. You can use a scientific model to help you communicate your ideas. The actual model of the atom is something to represent reality in a way we can understand, for example. It's not, you take a microscope, and we don't have microscopes like that you can get in the classroom and view atoms and stuff like this. It wouldn't look just like we have for the model. That just represents something so we can understand it better. It's an analogy. Anyways, the reason why is we can't watch electrons flow and see how electricity works, but we can understand water flow a lot easier. So we're going to do that with this, okay? So we're not doing a study question, but here's what they say. How can you use a model to help understand interactions among voltage, current, resistance? Here's what we're going to do. We've created the data table, number one. Number two, we've got tubing on the tap. I've got it. Okay. Without bending much. We're going to curl it a bit, but not a hard bend. We're going to turn on the water to a medium flow. Record the time it takes the water to exit the tubing. Tubing. Yeah, tubes. Pinch the end of the tubing. Turn off the water. Keep it pinched. Simultaneously, turn on the water to a medium flow and release the end of the tubing. Record the time it takes for the water to exit the tubing into the sink. Okay, those are the first two things. This is kind of like turning on the light switch. How quickly does the light turn on? Instantaneous. We're going to just see about this. And that's the purpose of doing this part. Okay? So I'm going to just pause, then the video. Okay. Now, nowadays, most of you have times, I see you have a phone right there. Are you good with timing? Trading or okay, Stelio, get your timer on. Okay, somebody else, come on. Okay, good. We'll do 2 or 3 people actually. Anyways, it's best if we have more than one time. They're not going to be the exact same. Sure, stop watching. Yeah. Okay. I'm gonna just see if this works. I'm not timing yet. I was just seeing how fast I turn it on. Okay. I'm going to turn it. I'm just getting this. I'm going to empty the tube though. Boy, there's a lot of heat. Okay, guys. Guys, I'll count us in. I'll go, Mark, set, go. On your mark, set, go. You guys, like when it started, did you guys get that?
Oh, like 5 seconds.
Did you guys start it? Did you guys follow what we were timing?
I thought you said.
Time to exit the empty tube. Like when it's said go.
Oh.
Okay, I'll do it again just so we know.
It did end up being like 5 seconds.
It is, but let's get at least somewhat in agreement. We're not going to get the decimals the same. Like the decimals the same way. Okay. We'll try this again. You guys are watching. When I say Mark said go, start timing. As soon as you see water just coming up, stop. We're not all going to be, but this is why we're doing multiple times, right? Okay. On your mark, set, go. So how about we're down to 4 seconds, and I hear anywhere from 4.3 to almost 4.5. Let's go to 4.4, 3.8, around. Let's go with 4.4 seconds. Does it sound reasonable? Okay. We could take the mathematical average, add them all up, divide by. But let's just. I actually didn't record that. I'm just going to say now. We did the first one here. I thought time to exit the empty tube. We did an average of multiple timings. It's 4.4 seconds is what we came up for an empty tube of this length. Time to exit the pinch tube. Now I'm going to fill the tube up with water, pinch it up, then turn it on and see how that times. And I think you guys have a prediction. What will that be? 6 seconds. 1 second. Remember, the tube is going to be full. I'm going to have it pinched off. Then turn it on.
Oh, so you go and then.
Time to exit the pinched tube. Okay. It might be instantaneous even. We'll see. So when we did this one, when the tube was already full, it was pinched off, and it didn't fly off the, right? We had 0 seconds. It's instantaneous. Now, time to fill the beaker with a pinched tube. What do we know though, when I pinch this tube, make sure it's empty. When I pinch this tube, okay, not pinched, what happens to the water speed? Right, this way, this way. And you used a good word, pressure. Which one's higher pressure, this one
No,
or the pinch?
it's like when just say, right, use a hose.
I'm gonna talk to you guys about pressure, but maybe not right now, because let's finish this right. Okay, okay, with the pinch two, and just so that the timing is right, I'm gonna pause that too. Okay,
Mine was just.
okay, we did this 23.5, and the tube was pinched. The water comes out fast, so when you use the word pressure, I'm not sure if we're using the correct way though. We'll talk about that probably tomorrow, once we have time. Now, we're gonna do the timing. Compare with the open tube right now. You guys think this will be faster, slower? How about this? Not speed. You think this will be more time or less time than 22 and a half?
It's gonna be slower because the water.
You mean it will be a greater number than 22 and a half?
Wait, actually no.
Somebody says the same. It could be faster, slower, or faster. Now remember, we're not accurately timing. If this is 22 to 25, we're basically the same. Right?
The pressure is the.
I don't know if we're using the word pressure right, but anyways, we'll talk about that later. Okay, let's go. On your mark, get set, go. You were right. 22.7. Would you say within the error of your thumb starting and stopping, this is the same? Okay, because we can do multiple trials, but I think it's 23. I'm gonna put 0.7 here is what I saw, but I mean, the decimal 7, decimal 5, so that's 22.9. It is more or less the same. Huh? Think about this thing. And we're just strictly talking about water. Tomorrow you can straight close your books or whatever, but tomorrow, time to fill beaker with water on full. This is good. We'll do this one right now. Sorry, because this will take. Now this time, I'm not going to go with this. Okay, let's just do this one. It's quick. Okay. Oh, right. I think you know this one. There's a tap on full blast. Right. Mark, get set, go. And
Yeah,
9.8, 9.7. And what about this if I pinch it? Get water. I'm going to do this one because it's going to be messier. Mark, get set, go. No, I can see it over there. It's flashing up so much, it's hard to tell. Okay? 10.4 RC. Okay, would you guys agree then, what was the other one, 9.17? Let's just put 10 and 10, because that one's so messy, it's hard to tell. And I actually couldn't stop because the water was, let's just put 10 and 10. It was the same for both, more or less. Put it on full blast. Put those ones on. And then we will talk about the data tomorrow.